This training session will cover Rego. Rego is a declarative language for defining policies. Rego policies are expressed as predicates over structured data. This structured data is represented using JavaScript object notation. This training covers the basic Rego features that will be needed to implement provenance policies. Policies in Rego begin with a head, which is the name of the policy. The head is followed by the body, which defines a list of expressions inside a pair of braces. Each expression in the body is evaluated to determine if the policy is true or false. For example, policy 1 on the right is true if all of the expressions 1 to n are true. Rego provides many operators seen in other languages, such as arithmetic, assignment, or equality. Note that variables are immutable, meaning they cannot be changed after their initial assignment. The example policy, named final policy, demonstrates comments, assignment, arithmetic, and equality. Final policy will always evaluate to true in this case. In Rego, arguments may be optionally passed to policies. The syntax is similar to functions in many other languages. For example, the following policy is 0 returns true if the argument x is equal to 0. Input is created using JavaScript object notation, or JSON. Provenance graphs can be defined as a set of vertices and edges. Each vertex contains a name and a type, and each edge contains a relation type, a source, and a destination. For example, the provenance graph below can be defined using the following JSON. The graph has two vertices and an edge between them. JSON data consists of a name and value pair. For example, name:\average is one such pair. There are two key value types needed for defining provenance graphs, objects and arrays. Braces define an object, and values can be accessed using the dot operator. Brackets define an array. The usual bracket notation can be used to access values in the array. For example, input.vertices bracket 0.name is average in the input on the right. This notation can be used in Rego. Now let's cover some common scenarios. The negation policy asserts that a policy or expression is not true. In Rego, this can be done using the not keyword. The not keyword can be followed by a policy name or expression. In the left example, the not keyword is used with an expression, while in the right example, it is used with a policy name. These examples are equivalent. The conjunction policy, also called AND, asserts that multiple expressions are true. Conjunction is implicit in Rego. For final policy to be true, both E1 and E2 must be true. The disjunction policy, also called OR, asserts that either expression E1 is true, E2 is true, or both E1 and E2 are true. For disjunction in Rego, define two policies with the same name. For example, the following two policies are named final policy. If either instance is true, then final policy will evaluate to true. The existential policy asserts that an expression is true for some variable of x. Variable x can be used in that expression. To define such a policy, the sum keyword can be used. The following policy requires there exists some vertex x named average. The vertex can be used as a placeholder to access arrays, as in this example. The universal policy asserts that an expression is true for every possible variable x. Variable x can be used in that expression. Rego does not explicitly support this. However, it can be accomplished by defining an existential policy and negating that policy. Final policy requires that, for all vertices x is not named average. This is done by defining average exists, a helper policy which requires there exists some x named average. Final policy then negates this helper policy. The edge policy asserts there is an edge between two vertices with a certain label or relation. Possible labels are was attributed to, was derived from, was generated by, used, acted on behalf of, was associated with, or was informed by. While Rego does not explicitly support this either, it can be accomplished using the sum keyword and the equality operator. The example policy requires an edge with label used to exist between the average and salary B vertices. To write a policy that combines the existential and universal policies in Rego, the policy argument feature is required. The following slide has an example. The following policy combines universal and existential policies. For all node agents, there exists some outgoing edge. The following Rego implements this policy. At the bottom, the has edges policy checks if vertex X has an outgoing edge. The node no edge policy returns true if there exists some node agent and that node agent has no edges. This is done by passing the node agent to the has edges policy and negating the result. Finally, similar to before, final policy negates the node no edge policy. If there is no node agent without an edge, then all node agents must have at least one outgoing edge, and final policy is thus true. Now let's go over some provenance examples. The following interface will be provided to implement your Rego policies. The left section provides a code editor with syntax highlighting to define your policies. Note, your final answer should be named final policy. This will be the policy used for determining correctness. On the right, the question and a few example inputs are provided. The inputs are provided in the JSON format seen earlier. You may switch between the different examples using the tabs above. Each input contains a note saying if it should or should not satisfy the policy. Finally, once you are ready to test your policy, you may use the Evaluate button below. If your policy is correct, you will be presented with a correct message. Write a policy to ensure that activity average use data entity salary B. First, let's take a look at the sample input. Input 1 has an edge between average and salary B, which is labeled used, seen here. As the hint suggests, this input should satisfy the policy. Inputs 2 and 4 should also satisfy the policy, while 3 and 5 do not. Since we need to check for the existence of an edge, we begin with the sum keyword to create variable I, like so. I represents some edge in the input. Using I, we place requirements on the edge by using the input keyword and accessing the edges array. Like so. In this case, we require that the relation be used, we require that the source be average, and for the destination to be salary B. We implement this like so. And finally, the destination. And perfect. When we click Evaluate, each possible value for I will be used until one is found that makes all three equalities true. If none is found, the policy evaluates to false. In this case, our policy works correctly for all 5 inputs, and you can see that we have received the correct message here. Write a policy to ensure that data entity average salary was not derived from salary C. For this policy, we need to check that for all data entities, average salary was not derived from salary C. Since this is a universal policy, we need to first define the opposite existential policy. That is, average salary is derived from salary C. The existential policy, named derived sal C, is very similar to the previous example. Sum X is used to find if there exists an edge with the correct relation, source, and destination. To finish, final policy negates derived sal C, returning true if average salary was not derived from salary C. Write a policy to ensure that activity average used key entity key B and key B was attributed to account agent Bob. For this policy, there are 2 different edges that must be checked for. One labeled used between average and key B, and one labeled was attributed to between key B and Bob. Since 2 different edges must be checked, the sum keyword is used to declare an X and a Y. The X is used to find if the edge between average and key B exists, and Y is used to find the edge between key B and Bob. If an X and Y can be found that makes these equalities true, then final policy returns true. Write a policy to ensure that there is some data entity the average salary was derived from. This example requires that an edge starting at average salary ends in a data entity. This requires us to check the vertex type, which can only be found in the vertex array. To do this, the sum keyword creates an x variable to represent the edge and a y to represent the vertex. The policy begins by finding an x such that the edge is labeled was derived from and begins at salary. Next, both x and y are used to find the destination vertex by comparing the name. Finally, the vertex type is checked. Write a policy to ensure for every data entity, if activity average used the data entity, then the data entity was attributed to either Bob, Alice, or Mallory. This policy requires all of the techniques seen earlier. First, this is a universal policy, as we must check every data entity. Thus, we first need the opposite existential policy. That is, one of the data entities was attributed to someone other than Bob, Alice, or Mallory. A helper policy, not BAM, will check for this. We will need to check two edges and a vertex for this policy. First, we use X to find the used edge from average, and then use Y to find the destination vertex. Y is then used to check the vertex type, and is then used with Z to find an outgoing edge. Z is used to check the edge label and that the destination is not Bob, Alice, or Mallory. To finish, the final policy negates the not BAM policy. In the case of an incorrect policy, an error message will be presented. Syntax or other errors in the code will be presented with a line number to help find the error. If the policy is valid but incorrect, the warning will list the inputs that did not pass.